Hello everybody. Um, this is a presentation about the solid software design principles. Let me straight away get in. So the motivation is basically to find some guiding design principles to maintain software quality over time. This was introduced by Robert C. Martin in Design Principles and Design Patterns. And in his work he observed some symptoms of rotting software design. So he observed that many projects over time the software would become rigid, which means it would be difficult to change the software or a lot of work to change the software. He observed fragility, which means that changes easily break the software. Immobility, which means that it was easier to rewrite than reuse parts of the software. And viscosity, which means that design preserving methods were harder to employ than hacks. And corresponding software development principles are to basically, instead of rigid, have flexible software. So we want to achieve that the software over time stays flexible, that it stays robust as opposed to fragile. And we want the software to be reusable as opposed to immobile. And instead of viscosity, we want software applications to be developable. So the solid authors are basically Robert C. Martin. He authored the Clean Code, Functional Design and other books as well. And here this is basically about the design principles and design patterns paper, which is based on his experience and on work by Bertrand Meyer, Barbara Liskov and Eric Gamma. And Michael Feathers, who is the author of Working Effectively with Legacy Code. He summarized Robert C. Martin's paper under the SOLID acronym. So the SOLID principles are 5 principles. S stands for single responsibility, O stands for open closed, L for Lisco substitution, I for interface segregation, and D for dependency inversion. So starting with the single responsibility principle, here's an example of a method which takes a list of people. It filters them for age at least 18, and it then prints out or puts these names into a HTML string. And then you can use this method like this. You can give it a list of people and say adults to HTML, and it will return a string. As you can see, this method is actually doing two things. It's filtering for adults, and then it's converting the list of names into HTML string. So this is not good. This method is responsible for two different things. It is better, obviously, to split this up into two methods. One for selecting adults. So this one will filter for people where the age is greater or equals 18. And then the second method, which is responsible for converting a list of people into a HTML string with a list of names. And then you can invoke it like this. So you first say select adults, and then you say people to HTML. This is a single responsibility. This is an example of the single responsibility principle. The next principle is the open-closed principle. It means the code should be open for extension and closed for modification. So this is an example which takes a list of shapes and then it checks the type of the shape. If the type is a circle, it will compute pi radius square, pi times radius square, which is the area of the circle. And if it's a rectangle, it multiplies the width and the height of the shape. The problem with this method is if we were to introduce another shape, another type of shape, we would have to modify this method. So this method is not open for modification, open for extension. It's also not closed for modification. We have to modify this method because it's not possible to, or it's not easy to extend this method. A better implementation would be this one, where we have a multi-method which dispatches the area multi-method, which dispatches on type of the shape. If the type is circle, it will compute pi times radius squared, and if the type is a rectangle, it will multiply the width with the height of the shape, and the total area is simply computed by applying the area method to each shape and summing the result. And the nice thing is this is open for extension, so we can just add another dispatch to the multi-method, the area method, and it's closed for modification. We don't need to modify this method anymore if we want to introduce new shapes. That was an example for the open-close principle. The next principle is the Liskov substitution principle. So here we have an example of, again with shapes, where we want to be able to set the shape. So if we have a rectangle, so we dispatch on type, set with dispatches on type of the shape. So if the type is a rectangle, we set the width. If the type is a square, we set both the width and the height, override it with a new value. Similar for set height. If the shape is a rectangle, we just set the height. If the shape is a square, we set both width and height to keep the size of the square equal. And then we can compute the area as before. We will make a dispatch, a multi-method, so that it's open for extension. And when we compute the area of the rectangle, we just say width times height. And if we have a square, we just say a square derives from rectangle. It'll use the same method then. And there's a problem with this code. And the Liskov substitution principle illustrates this problem, or defines this problem. The Liskov substitution principle states, among other constraints, that a subtype is not substitutable for its supertype if it strengthens its operations preconditions or weakens its operations postconditions. This is from Banyasat, making the Liskov substitution principle happy and sad. So basically what it means, as shown in this illustration, is that the precondition of the base class or base method must imply the precondition of the inheriting method, of the method of the inheriting object or class. And after executing the method, the postcondition of the substituted method must imply the postcondition of the original method. And in our example, we can show that this is not maintained anymore. So when the precondition is that width is W0 and height is H0, if we set the width of a rectangle, the width will now be W and the height will still be H0. The precondition for the square, the set width method of the square type is simply true, is always true. And when after setting the width of the square, we get width equals W and height equals W as well. And this does not imply the original post condition anymore, so the Liskov substitution principle is violated. So you have this very strange behavior that if we have a method which does some computation and uses set width on a rectangle, if later a square comes in, if this later square is substituted by the calling method, then these conditions will not be true anymore. For example, if we double the width of a rectangle, we expect the area to double as well, but if a square is substituted, then suddenly the area will be 4 times as much. So we can't reason very well about the code anymore. So a better implementation which fulfills this Liskov substitution principle is to say we implement set width and set height. We just implement it for the rectangle. And for the square we say set side instead. And we just have one variable which is the side of the square. And then we don't inherit the square from the rectangle. Instead we say we have two different implementations for the area, which are on different branches in the inheritance tree, basically. So if we have a rectangle, we say width times height is the area, and if we have a square, we say side squared is the area. And like this, the Liskov substitution principle is fulfilled. We simply make it we basically make it such that a square cannot simply be substituted for a rectangle anymore. The next principle is the interface segregation principle. It basically says that interfaces should be as small as possible, so you shouldn't have multiple things in an interface which are not which don't need to be in the same interface. So here we have an example of an account holder. The account holder has a name, an age, and a balance. And then we can, for example, check if the account holder is an adult by checking that the age is greater or equal to 18. We can deposit some amount in the account by updating the balance of the account holder with the amount, increasing it by the amount. And withdrawal is done by decreasing the amount. This implementation works, but it would be better if we would segregate the interfaces. So here we have separated the interface into two interfaces. One is the person and the other one is the account. So we've separated person and account, so we can now check whether a person is an adult, and we don't need to supply any account data like balance anymore. It's not necessary to know the balance of an account if you want to check whether a person is adult or not. And the account is separate from the person, so we can deposit and withdraw as before. And we can now have a person without an account and we also can have an account without a person, or we can have a person with multiple accounts. If we still want an account holder, we can, of course, say we have a person and an account, and we just dispatch through those two interfaces when we need information about whether it's an adult or whether if you want to deposit or withdraw. The final principle is dependency inversion. Dependency inversion basically says you should depend on abstractions to reduce the dependencies. So you depend, you don't have a tree, or you don't have a tree of code basically of dependencies, but you depend on very abstract interfaces, which makes it easier to replace some module with a different implementation. So here's an example where we print a list of names. So we take a list of people and we take a print writer. And now if we run this method with a person named Alice and a person named Bob, and we supply the standard output, we get the two names printed to standard output. However, it's possible and it's better to depend on a more abstract interface. So here we depend on writer, and the interface for writer is a bit more complicated. So we need to first write the name of the person and then write the new line character. The nice thing is you can still print names to standard output, but it's now also possible to print names to a file, because we decided to depend on a more abstract interface. We have now new possibilities where we can replace standard output with a file to achieve a different behavior. I found an interesting article, a nice article by Mike Lindner, the 5 principles for solid software design, and he showed a diagram where you basically can see the 5 aspects of a class. So you have in the center you have the purpose of the class, or maybe it's responsibility, and then you have the responsibility towards parents, to the implementation it's based on, and you have the responsibility towards inheriting code, towards inheriting classes, or to code which in turn builds on this implementation, and you have responsibilities towards callers. So you have an interface towards callers, and you also have an interface towards callees. And this is basically matching the 5 principles, the 5 solid principles. So for the class internal or method internal implementation, you have a single responsibility principle. For the class inherited from, you have the Liskov substitution principle. And the responsibility towards inheriting classes is the open-close principle. And for callees, you have the interface segregation principle. And for callers, you have interface segregation principle. And for callees, so method interfaces you call, you have the dependency inversion principle, depending on abstractions. So it's quite a nice way to memorize this, and it also shows that this is it really covers everything. These principles, they cover all the different interactions of a piece of code with other pieces of code. That's basically the solid software principles. Thanks for listening. And any comments, suggestions, and questions are welcome.